Hello again, welcome back. This is going to be the video on page 4 of Midterm 1 for Chem 3A Fall 2019. So starting with the first question, it says that we're looking at the first step of question 2A, and we're going to classify the reactant moles and identify the reactive orbitals. So we're seeing again that we've got this hydroxyl group right here. And so automatically we usually think of hydroxyl groups as bases, but they can also be nucleophiles sometimes. And that is actually going to be the case here because a base is something that takes a hydrogen away from an acid, or if it was acting as a base. It is a base, but in this case it wouldn't be a base because it's not taking away hydrogen, and it's also not giving a hydrogen, which is why we know it's not an acid, but it is taking its lone pair, and it's using that to form a bond with the carbon right here, which makes it a nucleophile, meaning in my head that it loves nucleuses, or it loves to make a bond to an atom. And so automatically we think like nucleophile, electrophile, so the thing that the nucleophile is attaching to is going to be the electrophile. But we can also double check that because this carbon right here is getting an electron attached to it. It's also moving an electron away from it, but that just happens as a result. It's really just wanting the attack with the electron, so it's an electrophile. And so it's asking what reactive orbital. And so because in the OH group a sigma bond is forming, we're going to say that the reactive orbital is sigma CO, because we are forming a bond between this carbon right here and the oxygen, and so it's going to be a sigma CO orbital that's reacting. And then over here on the left side, with our electrophile, we have a pi bond breaking and going onto the oxygen, the electrons that were in the pi bond. And so that is going to be the pi star CO orbital. Star because it's breaking instead of forming, and CO because it's the electrons between the carbon and the oxygen. Oh, sorry, not sigma CO. Sigma CO would be what is forming. That's my bad. It is the non-bonding lone pair in O. So we call that non-bonding OSP3 because it's these electrons right here that aren't in a bond. It's forming a sigma CO bond, but that is not the reactive orbital. That's not the electrons that are moving. It's the non-bonding pair in the oxygen, which is sp3 straight. My bad. Okay, so the next part says draw curved arrows and predict the resulting products for a single step reaction at a different site but with the same reactive rules. So we know that this is still going to be the nucleophile, and this is still going to be the electrophile. Oh, that's my mom. And it says compared to the previous scheme, hint compare to question 3A. So let's look back at question 3A. This is my work from the previous video. And 3A was where we drew the curved arrows and the resultant structures for the different resonance contributors. And so we can see that with this one, the carbocation formed in that spot instead of right here. So as you can see here, we were kind of looking, up here, we were looking at the electrons moving onto this oxygen and forming the carbocation here at the same time that the oxygen is attacking this carbon. But instead, we could have these electrons move over here and then the oxygen attack over there. Let's erase that because that's not for this step. That is for the next step. So that's what we're going to do. We're going to have this nucleophile attack the electrophile, which this carbon can be an electrophilic site because we can have resonance where this double bond moves here. We couldn't attack it really if there was no resonance, because then we would have a carbon making 5 bonds, and that just wouldn't be happy. And again, when we move these electrons, we also, right here, for the same reason, we don't want there to be 5 bonds to this carbon, so we have to move these electrons onto the oxygen, just like we did with this resonance contributor here. We moved the electrons over from one pi bond to the other pi bond, and then we moved these onto the oxygen. And so that is what we're going to do right here. Yeah, and so what is the product? It's going to be just like that one. We could even probably check with question 2a. Let's see, what does question 2a say? Yeah, it's like this one, where we're attacking with the OH. But we can figure it out without looking at question 2a. We can just attack over there. So we have our prime, our methyl group, sigma bond. We're not caring about stereochemistry, so we can just put the OH over here. We could put it over here too, but it just looks prettier to put it right there since we're not considering stereochemistry anyway. And then this pi bond there is gone, but there's one right here. There's a bond down to oxygen, which has a negative charge. So we moved a lone pair. We moved the pi bond onto that oxygen as a lone pair. And the rest of it stays the same. So that's the resulting product. So now on to part C. It says, first explain the difference in reactivity between the two ethers. So first let's find the two ethers. Ether, you'll remember, is where there's an oxygen sandwiched between two hydrocarbon groups, two R groups. And so let's look. There's one right here in that little triangle, and then there's one right here in the hexagon. So why do they have drastically different reactivity? Well, you might remember that there's something called ring strain, because these tetrahedral atoms, which are making 4 bonds, like to have each of their bonds about 109.5 degrees apart. That's how, I think that's how much it is. Maybe it's a random number. Hopefully I'm not wrong about that. Anyways, but it's something along those lines. Which is how far apart each of them are. That's why it's called a tetrahedral shape. It makes 109.5 degrees between each of the bonds, or 110 or something else. But this is an equilateral triangle right here. So each of these are 60 degrees apart. 60 degrees for each of these. That's so different from 109.5. That's really, really like putting a lot of strain on each of these bonds. It doesn't like to be like this. So that's going to want to break apart as soon as it can, whenever it can. So versus in the hexagon shape. So there's actually this interesting pattern with cyclohexane, or with other cyclohex kind of groups where there's 6 atoms in a ring, where each one, this isn't necessarily that important for this question, it's just important to know that these are in about the right degree. Basically, every other atom is going up and down. I guess I'll draw it the way we normally draw it. So each one of these is an atom we could make this one the oxygen or something. And so every other one is kind of pushed up and every other one is pushed down. It kind of rotates around, so it's like going up right here, it's going up right here. Sorry, let me highlight that to make it more obvious what I'm doing. It's going up right there, it's going up right there, it's going up right there, it's going down right here. So basically it ends up being about 110 degrees, about the right angle, so it's not putting a lot of strain on these bonds over here. Versus the triangle, lots of strain, lots of strain. This is not happy making. Actually I should erase that because we're gonna have to draw something in here. But yeah, so that's the main difference between these two ethers, is one of them is in a 6 cycle and one of them is in a 3 cycle. So when it's asking in this box why the two different ether groups have drastically different reactivity, it is because of ring strain differences. I'll say make left one or left ether more reactive. Maybe that's not what I would say in an exam, but yeah, the 3-membered ring is more reactive than the 6-membered ring because of the ring strain. It just doesn't want to be like that. So the next part is draw curved arrows corresponding to a reaction of the more reactive ether with hydroxide. So basically what's going to happen is we got this OH group right here, and we've got this epoxide right here that isn't happy at all. So we don't want to just like break one of these bonds onto the oxygen, because then we'd have a plus charge right here. So, well, we do want to do that, but we don't want to have the plus charge on the carbon. So at the same time as breaking that bond, we are going to attack the carbon with the OH group, so that the carbon never has a plus charge. The OH is attacking at the same time that the epoxide is breaking. This could also be from the other side. Doesn't matter which one you do. You could attack on this side and then break that bond. But you have to do it one way or the other. You can't do like attack on this side and then break this bond. That wouldn't really make sense. Then this carbon would have 5 bonds, 5 bonds right here and 3 bonds right here. That wouldn't make any sense. So you have to either do what I drew in black or what I drew in blue. So either way, the OH, the hydroxyl, is acting as a nucleophile again because it's using its lone pair to make a bond, attacking the nucleus. And this whole molecule right here is going to be the electrophile because it's taking a bond. It's taking some electrons for it. And the reactive orbital is going to be the one that's breaking over here. And so that would be a sigma bond is breaking, so it's going to be sigma star, and it's going to be CO because it's the bond between the carbon and the oxygen. Okay, the classify, we did part 3 of number C and letter C, and the last part is drawing the orbital interaction sketch. And over here it says substituents can be abbreviated. Don't draw the whole molecule, that would be so much to draw in this little box. So we are going to make our lives so easy. Well, not so easy, but you know, easy enough. And this is really the only thing that's reacting here, right? That, this carbon, this oxygen, and the OH. And so we are going to label the rest of the molecule as 2 different R groups. Let's call this one R1 and this one R2. And let's erase one of these. Let's erase the blue ones. Just because we have to only draw one of them for the orbital interaction sketch. Sorry. Sorry. Okay. Okay, so let's draw our equilateral triangle. Let's start with that. And then we're going to have oxygen at one of these corners. And we are going to break the bond with the carbon. So we're going to break this bond. Let's highlight it. We're breaking this bond. Breaking. This bond right here is going to stay the same, so we don't even need to worry about that. And this carbon is making a bond to the OH group. So we're going to draw our little OH over here. Oh, and we need to include our two R groups. Can't forget that. So since we drew the black arrows, it's R2 that's attached to the carbon that's breaking. So it's going to be right here. As you see, we labeled R2 over here on the right, and that is the one that's next to the carbon that's breaking. And then over up at the top, that's going to be our R1 group. Okay, and now we have to draw the orbitals. So we are attacking with the p electrons and oxygen. So we're going to draw a p orbital right there. And then we are breaking the sigma bond between the carbon and the oxygen, right? So we're going to draw, this is going to be an sp3 and another sp3 on the oxygen. And when they are breaking, we're going to have one lobe shaded, and we want to have them oppositely shaded, right? We want this to be opposite shading to show that it's breaking. And so this one right here is going to be not shaded, and then we want to show that this right here is forming. So since the OH, here, actually let's draw this hydrogen out of the way. Still attached to the oxygen, but not in the way of the orbitals. So we need to have this opposite one shaded, because with each atom we need to have one lobe shaded and one lobe unshaded, or we could do different colors, but in this case we're just going to do shaded and unshaded. So we're showing that this shading between these two lobes matches to show formation, just as these ones over here are opposite shading to show breaking. And it says orbital interaction sketch with shading and orbital labels. So this is going to be sigma star CO, like we said, and this is going to be non-bonding OSP3, because we're taking the electrons that are in the sorry, it's not in a p orbital, it's in an sp3 orbital. My bad. This is why I don't do orbital sketches very well. But yeah, the electrons are going to be in a non-bonding OsP3 orbital. So yeah, that's going to be that. I guess I should erase the unnecessary information for the answer so that you can see what the answer should look like. This is all just information to make sure you know you're right. Yeah, this is what it should look like, minus the green highlighting. I'm sure you won't get marked down if you highlight, but in this case. But yeah, so we showed, oh, that's not what we want to do. We showed the two orbital labels that are interacting here, and we showed all of the orbitals, making sure that we switch between shaded and unshaded for each atom. Each one has to have one side shaded and one side unshaded. Each of these are sp3, even though I drew them in varying sizes. Each one of these orbitals that I drew are sp3. And we are showing opposite shading for the breaking one, the sp or the sigma star, and we are showing matte shading for the new bond that's forming between the OH and the carbon. So that is page 4 of midterm 1.